Hi friends, welcome to my channel. Now we want to discuss about computer organization and architecture, machine instructions, types of instructions, 0 address instructions, 1 address instructions and 2 address instructions, 0 address instructions, NOP, 1 address instructions, push, pop, 2 address instructions, add, multiple, SUB. Addressing modes shows the ways where the required object is present. The object may be an instruct or data. Addressing modes are basically classified in two types. Sequential control flow addressing mode: when the program is stored in the sequential memory locations, the program counter itself points the next instruction address. Therefore, such addressing modes are focused on data. Transfer of control from flow addressing modes: when the program is stored in the random memory locations using structured programming, there is a need of special instructions and addressing modes in order to calculate the next instructions. Next, the sequential control flow addressing modes. Register based addressing modes. These addressing modes are used to access the data when it is available in the registers. Register or register direct addressing mode. This addressing mode is used to access the local variables. In this mode, the data is present in the register. The register address is available in the address field of the instruction. Therefore, the effective address is equal to address field value data equal to brackets lo EA that equal to register name brackets. Example, move R1 R2. Example, move R1 R2. Memory based addressing modes. When the data is available in the memory, different memory based addressing modes are used to access the data. Under this, the EA is always the memory address. Implied or implicit addressing modes: in this mode, the data is available in the opcode itself. Therefore, there is no effective address. Example, complement, accumulator, CMA and all 0 address instructions. Immediate addressing mode: this mode is used to access the constants or to initialize the registers to constant value. Here the data is present in the address field of the instruction. The range of values initialized is limited by the size of the address field. If the address field is size n bit, then if the address field size is n bit, the possible range of immediate constants or data is 0 to 2 power n separate -1. Example, move A, 10H. Direct or absolute addressing mode used to access the static variables. The data is present in the memory. That memory cell's addresses is present in the address field of the instruction. Data equal to brackets like EA that equal to memory's address in brackets. One memory reference is required to read or write the data by using the direct addressing modes. Example, move R1 1000 in brackets. Auto indexed addressing mode. This mode is used to access the linear elements. Thus, base address is required to access the data. The base address is maintained in the base register. Therefore, the EA is a base register plus or minus step size. Step size is dependency on the amount of the data to be processed from the memory. Data equal to EA equal to in brackets base register plus or minus step size. Close. Now, auto indexed AM. The two types: auto increment, auto decrement. Auto increment two types: pre auto increment, move R0 plus R1. లేదా పోస్ట్ ఆటో ఇంక్రిమెంట్ మూవ్ R0 R1 ప్లస్. అది సేమ్. ఆటో డిక్రిమెంట్లో 2. ప్రీ ఆటో డిక్రిమెంట్ మూవ్ R0 మైనస్ R1. పోస్ట్ ఆటో డిక్రిమెంట్ మూవ్ R0 R1 మైనస్. Indirect addressing mode: array as parameter used to implement the pointers. The EA is available in either register or memory. This mode is divided into two types: register and indirect addressing mode. Here the EA is present in the address register. The register name is available in the address field of the instruction. EA equal to address field value that equal to register name. Memory indirect addressing mode: here the EA is present in the memory. That memory address is available in the address field of the instruction. EA equal to address field value that implies memory address. Data equal to EA equal to memory address. Two memory references are required in memory indirect addressing mode. Indexed addressing mode allows to implement array indexing. EA equal to base address plus index value. The register that holds the index value is the register indexed addressing mode. It is used to access the random array element. In the indirect index addressing mode, the base address is present in the memory. That memory address is present in the address field of the instruction. Transfer of control flow addressing mode. Transfer of control flow addressing mode. During the execution of selection statements, if, then, else, go to, switch, iterative statements for loop, while loop, do while loop, and a subprogram concept, the control is transferred from one location to another location. Transfer of control operations can be implemented by using three possible mnemonics: jump, branch, and skip. Transfer of control instructions is divided into two types: unconditional transfer of control. While execution of these instructions, the program control is transferred to the target address without checking any conditions. Example, HALT. Conditional transfer of control. While execution of these instructions, the associated condition undergoes evaluation. If it is evaluated to true, then the target address is loaded into program counter PC. Else, no change in PC. The condition can be evaluated based on the status of the previous instruction. Example, they are used to implement if, switch for do while, and while statements. Instruction set equal to opcode vector interrupt. Interrupting source applies branch infet processor through an interrupted vector. INTA bar is nothing but INTR. Computation of EA for the next instruction relative or PC relative addressing mode. Relocation data. Branch address at runtime. Reduce instruction size. This addressing mode is used to access the instruction within the segment. Therefore, only the offset address is required. The offset address is available in the address field of the instruction. EA equal to base of address plus offset address means PC. Offset address means address field value. PC లోకి అసైన్ చేయాలి. PC plus IR. IR in brackets address field. Position dependent relocation at runtime. Base register addressing mode. Brackets లో position independent. The addressing mode is used to access the instruction between the segments. Therefore, base address as well as offset are required. Base address is maintained in the base register and offset address is maintained in the address field of the instruction. EI equal to base register plus IR address field. PC means base register plus IR address field. Alien data path. CPU control design. This CPU divided into two sections: data section and control section. Data section also called as data path. The control section is control unit. Data path contains registers and ALU which performs certain operations on data items. Control unit issues the control signals to the data path. ALU and data path. Types of data path: 1 bus data path, 2 bus data path, and 3 bus data path. In 1 bus data path, CPU registers and ALU use same bus for all incoming and outgoing data. In 2 bus data path, general purpose registers are connected to 2 buses. Data can be transferred from 2 different registers to the input point of the ALU at the same time. In 3 bus data path, 2 buses are used as source, moves data out of registers, while the third is used as destination, moves data into registers. Source bus is also called as in bus and destination bus is also called as out bus. Okay na. General purpose registers PC, IR, MAR, MDR, AB, ALU. Data bus is bidirectional bus. The ALU registers and interconnecting path is called ALU data path. Constant is used to increment PC. If select equal 0, output of mux is constant. If 1, output of mux is Y. CPU registers PC. It is used to hold the starting instruction address and immediately point to the next instruction address. IR. It is used to hold the currently fetched instruction to decode as instruction format defined in this register. Therefore, it is not a user accessible register. Accumulator. It is used to hold the one of the ALU input and output. MER, memory address register. It is used to carry the address. This register is directly connected to address lines of system bus. MBR, memory buffer register, or MDR, memory data register. It is used to carry the binary sequence. This register is directly connected to the data lines of the system bus. Micro operation. It is a basic register to register transfer operation, also called as automatic operation or control mode or micro instruction. All the micro operations must complete the operation in one cycle. Control signals are required to execute the micro operation. Example, R1 tends to R1, R1 tends to R1, R1 out, R2 in. Microprogram. The sequence of micro operation is called as the microprogram. The fetch cycle microprogram is T1, PC, MAR, PC tends to MAR, PC out, MAR in. T2, M of MAR tends to MBR, MAR out, MBR in. T3, MBR tends to IR, MBR out, IR in. PC plus step size tends to PC, PC out, PC in. The basic operations performed are register transfer. R2 tends to R1, R1 out, R2 in, only one clock cycle required. ALE performance R1 plus R2 tends to R3, R1 out comma Y in, R2 out select equal to 1, add Z out R3 in, minimum number of clocks equal to 3. If two data paths are used, R1 out comma Y in comma R2 out select equal to 1, add Z out R3 in, minimum number of clocks equal to 2. Memory read M of R1 tends to R2, M1 out MAR in read, wait for memory function to complete WMFC, MDR out R2 in. Here number of clocks can be 2 or 3 depending on WMFC. Memory write M of R1 tends to R2, R1 out MAR in, R2 out MDR in, write WMFC, minimum number of clocks equal to 3. Control unit. The purpose of control unit is to provide appropriate timings and control signals which are required to execute micro operations. Control signals are directly executed on the base machine. Microprogram contains sequence of micro operations. Subcycles of instructions cycle invokes their own microprogram. Instruction cycle is used to execute one instruction. System functionality is execution of the program. Program is a sequence of the instructions along with the data. The purpose of control unit is to provide appropriate timing and control signals which are required to execute micro operations. Control signals are directly executed on the base machine. Microprogram contains sequence of micro operations. Subcycles of instructions cycle invokes their own microprogram. Instruction cycle is used to execute one instruction. System functionality is execution of the program. Program is a sequence of instruction along with data. Execution of the program, system, program, instruction cycle, microprogram, control unit. Program execution using control unit. Now, next concept is control unit design. Control unit have two types: hardwired approach, microprogrammed approach. Microprogrammed approach has two types: horizontal programming, vertical programming. Hardware control unit. The control signals are expressed as sum of products expression and they are directly realized on the independent hardware. Example: Yin equal T1 plus T3 into add plus T5 into BR and so on, where Yin is enabled during T1 for all instructions, during T3 for add and so on. It can be realized as it is the fastest control unit design because of independent circuits. For large number of instructions and control signals, the complexity of hardware is more. Relatively inflexible for any of the changes like modification, recorrection, thus it is not used in the design and testing places. Used in real-time applications, example aircraft simulation and weather forecasting, etc. Implemented in RISC processor. Next heading is microprogram control unit. Control memory CM is used to store the microprogram. Control memory CM is a permanent memory, that is ROM. Microprogram contains sequence of micro operations control word. The format of the control word is branch condition flag, control field, control memory address. Branch condition, number of branch conditions. Flag means flag information. Control field means control signal CS. Control memory address, new next micro operation control word address. Control field CS are stored in first one decoded format 1 bit per second per CS. Horizontal CW, encoded format and control signals required log and base 2 bits. Vertical CW. Next micro operation control word address means capacity of the CM. Flexible for large number of instructions and CS. Control signals are generated slow in comparison to hardwired. Based on the type of control word stored in the control memory CM, the control is classified into two types. First one, horizontal microprogram control unit, HMU PCU. Vertical microprogram control unit, VMU PCU. Horizontal MU PCU. The control signals are represented in the decoded binary format, that is 1 bit per chip second CS. Example: if 68 CS are present in the processor, then 68 bits are required. More than one CS can be enabled at a time. It supports longer control word CW. It is used in parallel processing applications. It allows high degree of parallelism. If degree is in NCS are enabled at a time. Requires no additional hardware decoders. That implies faster than vertical MU PC. Vertical MU PC. The control signals are represented in the encoded binary format. For n control signals, log n base 2 bits required. Example: if n equals 68, then log 68 base 2 equals 7 bits required. If it supports shorter control word, it supports easy implementation of new control signals therefore it is more flexible. It allows low degree of parallelism, that is degree of parallelism is 1 or 0. Requires an addition hardware and decoders to generate control signals. It implies lower than horizontal mu PCU. The ascending order of control unit with respect to speed vertical less than horizontal is less than hardwired highest. The ascending order of the control unit with respect to flexibility, low flexibility hardwired less than horizontal less than vertical. Risk difference same. Reduced instruction set is set computer supports register set, supports less number of addressing modes. RISC supports fixed length instructions. RISC one instruction per cycle, CPI equal to 1. RISC allows successful pipeline implementation, CPI equal to 1. Example Motorola PowerPC advanced RISC machine. Whereas CISC complex instruction set computer, CISC supports less number of registers. CISC supports more number of addressing modes. CISC supports variable length instructions. CPI is not equal to 1. CISC successful unsuccessful pipeline, CPI is not equal to 1. Example Pentium. Next, memory and input output interfaces. The isolated input output CPU has distinct instructions for memory read or write and input output read or write. The address what we use for accessing a device may be same as one of the address in the memory. However, separate lines are used to indicate input output device address. In memory mapped devices, their interface registers are memory mapped on the address space of the memory. Input output organization. Input output devices are very slow devices, therefore they are not directly connected to the system, but because input output devices are electromagnetic devices and the CPU is the electronic devices, there is a difference in the operating mode, data transfer rate and word format. To synchronize the input output devices with the processor, there is need of high speed interface input output module. The high speed interface enables the corresponding device for the operation. After preparing the data, the input output device transfer it to the buffer. When the data is present in the buffer, then the high speed interface generates the signal to the CPU and waiting for the acknowledgement. After receiving the acknowledgement, it transfers the data to the CPU with high rate, thus the speed gap is minimized. Types of interfaces. Non-programmable, programmable. Non-programmable configuration is predefined during the design time that can't be changed during the operation. Example, buffer latch. Programmable configuration is defined in the command word register. Based on the value loaded into the CWR, the configuration is changed. Programmable serial interface, parallel interface. Serial interface lo bit by bit transmission. Example 8251 USART, universal synchronous asynchronous receiver transmitter. Parallel bit lo more than one bit transmission. Example 8255 PPI, programmable peripheral interface. 8259 IC, interrupt controller. 8237 and 8257 DMA. Input output transfer modes. 3 different modes available to transfer data from input output to CPU or memory. Programmed input output. Here the CPU directly communicate with the input output device, hence the processor utilization is inefficient. The processor undergoes waiting until completion of the operation. This waiting depends on the speed of the input output device. Interrupt driven I/O. Interrupt controller IC is used as high speed interface between the basic input output device to CPU, hence the processor utilization is good or efficient. Here the CPU is communicating with IC only, thus the execution or transfer time is not depending on the speed of input output device, rather it depends on the latency of IC. CPU byte level IC, input output 1 kbps, input output 10 mbps, input output 50 kbps. Direct memory access DMA, the bulk amount of data is transferred from the input output devices to the main memory without involvement of CPU. The secondary storage devices are connected to the system but bus through DMA, while execution of user program from the auxiliary memory to main memory, the program is transferred page by page through the DMA. The CPU initiates the DMA along with source and destination address, control signal and count value. Later it is busy with some other execution based on priority daisy sign, non-uniform priority to each device polling. RFE is top privileged instruction. The DMA control logic interprets the request and enables the corresponding device for the operation. After preparing the data, device transfer it to the buffer. CPU memory system bus DMA, control logic buffer, input output. When the data is available in the buffer, then DMA enables the hold signal to gain the control over the bus and waiting for the acknowledgement. CPU hold HLDA that is connected to 8237 or 8257 DMA control logic buffer, secondary storage components. After receiving the HLDA signal, the DMA transfers the data from input-output device to main memory until the count becomes 0. After transfer operation, it establishes connection to a CPU. During the DMA operation, the CPU is in two states, busy state, block or hold state. Until preparing the data, the CPU is busy with other executions. While transferring the data, the CPU is in blocked state. Let x equal preparation time depends on input-output speed. Y equal transfer time depends on main memory speed. And percentage time CPU is blocked equal to y by x plus y into 100. Percentage time is CPU is busy equal to x by x plus y into 100. DMA operated in three modes. Burst mode, after receiving the HLDA signal, bulk amount of data is transferred to main memory. Cycle stealing mode, before receiving the HLDA signal, it is forcefully suspend the CPU operation and transfers very important data to the main memory. Block mode, after receiving the HLDA signal, the data is transferred to the main memory in block-wise. Instruction pipelining, the set of phases for an instruction execution cycle. Instruction fetch IF, MAR, PC tends to MAR, 2000 tends to MAR, PC plus 1 assigns PC. Next instruction 2004, read control signal is enabled. MDR assigns IR, IR loki MDR vastadi. Instruction decode ID to know the purpose of instruction. Operation fetch OF, memory read. LOCX tends to MAR, write into any general purpose registers. MDR tends to RI, execute and store EX. LOCZ tends to MAR, RI tends to MDR, write into memory. Indirect phase, interrupt phase. Each instruction cycle involves a sequence of micro operations to be implemented by the processor. A micro operation is register transfer operation, completes in one clock cycle. If T is the total time for the instruction cycle, the T will be divided into T1, T2, T3 among different phases. The CPU is operated in two modes, user mode or non-privileged mode, executes user program. System mode or supervisory or kernel or privileged mode, executes operating system to obtain system services. Types of interrupts, external or hardware interrupt arise due to timing and input-output devices. Software interrupt arise due to switching from user to system mode or vice versa. Internal interrupt arise due to incorrect use of instructions and data. Example, division by 0 register overflow, invalid opcode. Pipelining, accepting new input to one end before previously accepted input but appears as an output at the other end is pipelining. Pipelining allows overlapping execution. The successful characteristics of the pipelining is for every new cycle, new input must be inserted into the pipeline. CPI equal to 1. Diagram is stage segment S1 R1, stage segment S2 R2, stage segment R3 output. Okay na. Types of pipelines, linear pipeline, non-linear, synchronous, asynchronous. Linear pipeline, this pipeline is used to perform only one specific function. Non-linear pipeline, this pipeline is used to perform the multiple functionalities. It uses feed forward and feed backward connections. Synchronous pipeline, on a common load or clock, all the registers transfer data to the next stage simultaneously. Asynchronous pipeline, the data flow along the pipeline stages is controlled using handshake protocol. Now, performance evaluation of pipeline processor. Consider k segments pipeline with the clock cycle time TP used to execute n tasks. The first task is executed in the non-overlapping time spent, so it requires k cycles to complete the operation. The remaining n-1 tasks emerge from the pipe at the rate of one cycle per task, and so n-1 task requires n-1 cycles to complete the operation. Thus, the execution time of the k segment pipeline ET pipeline equal to k plus n-1 cycles. ET pipeline equal to k plus n-1 into TP. K plus n-1 అంతా ఒకటి, దాని పక్కన ఇంటూ సెపరేట్గా TP. The performance gain of the pipeline processor over the non-pipeline is speed up S equal to performance pipe by performance non-pipeline 1 by ET pipe whole by 1 by ET non-pipe, that equal to ET non-pipe by ET pipe. S equal to NTN by K plus n-1 ఇదంతా ఒకటి into TP. For large number of tasks or instructions, K plus n-1 approaches to N. S equal to NTN by NTP, S equal to TN by TP. When all the instructions are taken in the same number of cycles, then one instruction's execution time is equal to the number of stages in the pipeline. K Tn equal to KTP equal to S equal to KTP by TP equal to S equal to K. Instruction pipeline. The instruction pipeline operates on a stream of instructions by overlapping the phases of instruction cycle, like instruction fetch, instruction decode, operand fetch, execute, memory access, write back, and so on. Performance evaluation of pipeline processor completed na. Next comes under stall cycle. A stall cycle is one during which no meaningful operation performed for an instruction. It arises due to uneven clock cycles needed by each stage for instructions, increased buffer overhead, memory operands, pipeline dependencies. S effective equal to S ideal by 1 separate plus stall frequency into stall cycles, that equal to K into number of stages by advanced pipeline. RISC pipeline. The RISC processor instruction pipeline is implemented to execute the instruction. RISC processor supports 3 categories of instructions. Okay, na data transfer. Data transfer instructions can be implemented by using load and store. Load R0, to R1. M of 2 plus R1 tends to R0. Store 3R to R1. M of 3 plus R2. R1 tends to M of 3 plus R2. Data manipulation, ALU operation is directly performed on the registers. We had R0, R1, R2, R0, R1 plus R2. R1 plus R2 tends to R0, R1, R2. That means R0. Branch operation, the unconditional branch operation syntax is jump 1000. Target address tends to PC. Conditional branch operation. JNZ R0 2000. Target address PC true. Sequential address P false అయితే sequential address అనేది పోతుంది. In this pipeline, the branch instruction execution is completed at the end of the stage, second stage. So branch penalty 2 minus 1 equal to 1. Register renaming can eliminate the all WAR hazard and WAW. Bypass cannot handle all RAW hazard. Memory load instructions, control hazard penalties can be eliminated by dynamic branch prediction. Dependencies in the pipeline. Dependency causes stalls in the pipeline. Stall is an extra cycle created in the pipeline with NOP. There are 3 kinds of dependencies possible in the pipeline. Structural dependency. This dependency is present because of resource conflict. The resource may be a memory, a register, or functional unit. Conflict is an unsuccessful operation, so to make it successful, make the instruction wait until the resource become available. This waiting creates stalls in the pipeline. To minimize the number of stalls in the pipeline due to the structural dependency, renaming concept is used. Register rename decrease equal to RAW. All decrease brackets removed equal to WAR. Data dependency consider the program segment. I means instruction, J means instruction. Data dependency exists between I and J when the instruction J tries to read the data before instruction I writes it. Control dependency. When execution of transfer of control, okay, na operation, the program control is transferred from the current location to the target location. If the current instruction is decoded as a data transfer or data manipulation operation, then the sequential instruction is wanted instruction. The process of removing unwanted instruction from pipeline is called as flush or freeze. Flush operation creates stalls in the pipeline. The number of stall cycles created in the pipeline due to branch operation is called as branch penalty. Branch penalty equal to what stage the target address is available -1. To reduce the number of stalls in the pipeline due to the branch operation, branch prediction buffer or loop buffer or branch target buffer is used. Branch target buffer, it is the high speed buffer maintained at the instruction fetch stage to store the predicted target addresses. The out of order execution creates 2 more dependencies in the pipeline. Anti-dependency, it exists when instruction J tries to write the register before instruction I reads it. Output dependency, it exists when instruction J tries to write the destination before instruction I writes it. To handle the anti and output dependencies, the register renaming concept is used. Register renaming means use the temporary storage to hold the out of order execution output. After receiving the execution exception from the dependent instruction, update the register file with temporary storage content. Hazard is a delay. Delay creates extra cycles. These extra cycles without operations is called as stalls. Hazards are classified as read after write, write after write, RAW, write after read, WAR. Consider a program segment where the instruction J follows the instruction I in the program order RAW. This hazard is created when instruction J tries to read the data before instruction I writes its true data dependency. WAR. This hazard is created when instruction J writes the data before instruction I reads its anti-dependency. WAW. Instruction J writes the data before instruction I writes its output dependency. Performance evolution of the pipeline with stalls. S equal to numerator part చెప్పేస్తా CPI non pipe into cycle time non pipeline by CPI pipeline into cycle time pipeline. CPI pipeline into cycle time pipeline is the denominator. For ideal CPI pipeline equal to 1. S equal to numerator part చెప్పేస్తా CPI non pipe into cycle time non pipe whole by denominator ideal CPI plus number of stall cycles by instruction. Number of stall cycles by instruction మాత్రమే ఉంటుంది. Whole into cycle time pipeline. When there is no setup time overhead, then both the cycle times are equal. So S equal to CPI non pipeline whole by 1 separate plus number of stall cycles by instruction. రెండు ఒకటి. Number of stall cycles by instruction. When all instructions are taking the same number of cycles, then one instruction requires cycle equal to number of stages in pipeline to complete the instruction execution. S equal to numerator part pipeline depth, denominator plot 1 separate plus number of stall cycles by instruction. Number of stall cycles by instructions is separate. When efficiency is 100%, no stalls. S equal to pipeline depth. Instruction pipeline can create one or more stall. Since register rename can eliminate it also. So always get false.